That's loud. Sorry.
All right, so welcome everyone. Thank you for joining us, and I am excited to introduce Jeroen Audenaert, a postdoc at MIT working with TESS, and he's going to tell us about how to use machine learning to find TESS transits.
Perfect, thank you. Hello everyone. I'm currently at MIT as a postdoc, as said. I started there in the fall, and before I did my PhD in Leuven in Belgium and spent a year at MIT as well as visiting machine. Today I will talk about specifically how we're using machine learning for stellar variability, and particularly for pulsating stars by using the TESS data. Let's see if this.
No, there's you're just not in the
right.
there.
Perfect. Well, there was supposed to be a video of TESS, but that's probably not showing up now, but I'll just explain. So essentially, TESS is a full sky survey that's scanning the sky in a sector of 27 days at a time, and it was particularly designed to look for exoplanets as a first site. But it's also very optimal to study all different types of stellar variability. And so here I'm showing a single sector of TESS data. So it has 4 different cameras. Each camera shows has 4
Sorry,
CCDs.
the screen sharing on Zoom stopped. Sorry, thank you.
Is it fine now? Or, I mean,
No, it's still not showing.
Yeah, I got it.
Then I guess we have to go back to that one.
There we go.
Should
Okay.
It's good now.
there you go.
Okay, perfect. Yeah.
Yeah, but it was not moving to the next. Can you try to go back over? Oh, yeah, it did.
The next one? Okay, perfect. Okay, yeah. So essentially, TESS scans the sky in sector of 27 days at a time. And here you can see a nice image. Otherwise, in the video, we'll actually see that it's moving around. And it does this in first the southern hemisphere, then the northern hemisphere, and essentially it switches up. At the moment, we're taking pictures or full frame images at a cadence of 200 seconds. And this is perfect for stellar variability. Now, we have about, for one sector is 27 data set, and then we switch to the next field of view. Now, we also have an overlapping zone where we actually have data up to 1 year at a time, which can actually give us more accurate results for stellar variability, essentially. Now here, I'm showing you a nice image of the TESS of a TESS full frame image. So you can see here one picture and then so one camera, 4 CCDs. And what we try to do is identify each single star in these pictures and then measure the brightness over time. Now, in particular, as I said, we want to use this for stellar variability. And stellar variability can be caused by multiple phenomena. The first one is, of course, you have extrinsic stellar variability. For example, this can be due to a transiting planet or also an eclipsing binary system. And here, the variability is caused by external changes. Now, what I'm particularly interested in mostly is intrinsic variability. So the variability that we observe through a change in brightness is actually caused by physical phenomena of the star itself. And in particular, we're looking for pulsating stars. Now, I had a very nice animation of pulsating stars, but it's not showing up here, given that it's a PDF slide. But essentially, stars pulsate, so you can actually see deformations on the stellar surface that we can actually observe as changes in brightness over time. I think maybe somewhere else I have a better one, but yeah, given that the animation is not loading, we'll have to do this. So what we do is we measure the brightness of all these stars. So of a variable star by selecting the pixels that are actually that are there for a particular star. We make an aperture mask, and then we get all these different light curves, as you can see here. Now, in a single sector of TESS data, we have about between 1 and 4 million light curves, depending down to which magnitude we go to. And the best way to actually process all these data and find the different types of variable stars, and in particular pulsating stars, is either machine learning, or otherwise you could also use citizen science. But citizen science is a bit more difficult if you have multiple variability types, because you would have to train all the citizen scientists to actually be able to identify the different variability types. I think for like, if you do it for transiting planets, it actually works well, because it's only one specific type of variability. But in our case, we have many different ones. So here, I'm showing kind of the variety of the variability we're interested in. And training people, if you would use citizen science to do this, is actually quite complicated because even for astronomers, we did some experiments, it didn't turn out to work very well, and we needed a lot of people to actually be able to get confident predictions for each type of variable stars. And therefore, we developed a machine learning classifier to essentially do this. And here I'm showing the variety of the different light curves we're interested in. So this, for example, is the light curve of a delta Scuti star, which is a type of pulsating star. And this is another type of pulsating star, for example, a gamma Doradus star. You can see all these different light curves are slightly different. Some are more easier or more difficult to recognize purely based on the time domain. For example, solar light oscillations are very similar by just looking at the time scale, by just looking at its light curve compared to constant stars, where we essentially see nothing at all. But if you would look in the Fourier domain, for example, then you could actually easily disentangle the two. Now, so what we did is we developed a machine learning classifier, as is illustrated here by this beautiful robot. And specifically, we're making use of two types of machine learning. We have supervised and unsupervised learning, where we use supervised learning to first get a high-level classification according to the first variability types I was showing. And this allows us to actually structure the data in a more easy way because we have 4 million light curves in a single sector. So then we have some idea what the potential type of variability is already. Then if we afterwards run unsupervised learning on top of that, that actually makes it easier because then we can actually look for more subclasses that are in there. We can look for new types of subclasses, and we can actually identify misclassifications even.
So can you get new classes or just subclasses? Like, could you?
So with the unsupervised one, you can actually get new classes of variability that are not in the supervised case.
Once you train it for the classes you know, then you release some, you add to the code.
Yeah, exactly. So what we essentially do is, like, let's say we get a catalog of pulsating stars. So we have gamma Dor stars, for example, that are returned by the supervised case. And now we run an unsupervised classifier on top of this, on top of these classifications, and kind of try to get the underlying structure without giving any information. So essentially, the supervised label acts as some kind of prior, where all the variability types that look like gamma Dor pulsations are grouped together. But by then running the unsupervised classifier on there, this allows us to actually just substructure, get the subclasses back, and we're not like enforcing any pre-known labels, but it essentially allows us to get subclasses, new types of variability, essentially. I have mostly focused on finding existing ones, but it should be possible perfectly to find these new classes as well. Now, just diving a little bit into our supervised classification scheme, we developed a couple of ones, but here is the architecture. So what essentially we do is we get the light curves from TESS, and then we feed them to 4 different classifiers. So each classifier uses a different set of features, and most of them use different types of algorithms. Now, for example, in this left one I'm showing here, what we do is we calculate the Fourier spectrum, here the amplitude spectrum, and then we feed this as an image to a CN network. In the other ones, we do some different ones. For example, here we have a random forest, and there we feed the skewness, for example, together with a couple of other features. And now we have other classifiers where we have XG boost and another random forest, but each of those classifiers is essentially specified in identifying a particular type of variability. So we essentially get for a single light curve 4 different predictions. And each classifier outputs 8 probabilities, a probability for each of the classes I showed before. Now what we then do is we take these 4 times 8 probabilities and we feed them to another classifier using a technique called stack generalization. Essentially, we're creating an ensemble model. So it's actually an ensemble of ensembles, given that we're already using random forests here. But this classifier, this meta classifier, learns the strengths and weaknesses of each of the underlying classifiers and finds when to use which particular classifier. So for example, this one is very good at identifying solar light oscillations, while this one is much better at identifying eclipsing binary systems and pulsating stars, for example. Now, this methodology is working quite well, but the downside of such a big methodology is also that it's actually quite computationally intensive. And if we have to process millions of stars, it's not always efficient if you want to look for a new type of star. So therefore, we actually developed another classifier just recently as well. It's slightly less accurate, but we see it's very computationally efficient. So for the previous one, it takes about a second, maybe 2 seconds per light curve. This one, to actually calculate everything, I think the downs is probably 1,000th or 1/10,000th of a second. And this is ideal for TESS. If you want to do a quick search for everything, then we can actually do this very easily. So the bottleneck of this architecture is actually just the reading of the input light curve files. The calculation goes very quickly, but it's less accurate. What we do here essentially is we have the light curves, and then as a feature representation, we calculate something that's called the wavelet scattering transform. It's an online library that you can easily use. And then we get these wavelet coefficients, and we feed these just to a simple, fully connected network. We're still optimizing this architecture, but for now, we see that it's about 5% less accurate compared to the other classifier, but it's much quicker. And therefore, this architecture is actually quite nice if we have a new type of variable stars that we want to look for. We don't want to spend too much computational resources, and this is one of the nice ones we can actually use for that as well.
So could you learn that representation instead of choosing the wavelet?
You could probably also learn such a representation, I think. So you could also just get a CNN or something to actually, or a transformer-based model. Essentially, you could use a transformer probably to replace that as well. So I think definitely this is not one. It's not a perfect solution, but it's just one of the opportunities you could do. But it's definitely if you train a different type of model, you can do like full self-supervised learning, I would say as well. The reason why we chose for this one was mostly because of the computational efficiency. And then if you want to learn a representation, the question is, what do you want to do with your light curve? Do you want to phase fold them? Do we use the full light curve? So there's kind of some added step that you want to add to that as well. So that's why we opted for this one for now. But we're also exploring many different ones, for example, based on transformer models.
Yeah, just one question. You mentioned that you feed into the CNN, you feed in image. Is that correct? Of the spectrum, what's the reason for this?
Essentially, yeah. So we transform it into a NumPy array, essentially. But that actually helps. It seems to be working very well. So it's essentially just an image of this one. Essentially, by feeding this 48 power spectrum, it essentially captures all the different types of oscillations. And that's why we specifically use this representation. It's just one way to essentially capture the structure of the light curve.
It was just wondering when you could feed in this spectrum just as a 1D area, right? I mean, I wouldn't say like any gain of information if you put in an image, right? Of the...
Yeah, exactly. So we are just feeding it as a 2D NumPy array, essentially. But you could also, I think it depends on the frequency resolution as well. But if I'm correct, I think it's a 2D NumPy, but you could probably feed it in a 1D as well. I would have to take a detailed look into the architecture exactly what we're doing, but I think you could do that as well. Because essentially, what you're right that you just need to get the amplitudes. Essentially, all of them are on the same spectrum. So
I think that's all the information you need.
Yeah, exactly. I think I would have to take a look what exactly we're doing there, but it might be that we use a 1D array. I thought it was a 2D, but it might be that you're right.
You go to the next slide.
Yes.
I was wondering, among the classes that you show at the bottom right, what kind of class imbalances do you see in nature, and do you try to mitigate that in training with this?
Yeah, that's a very good question, because there's actually a lot of class imbalance, and I think what the tricky thing is for us, I mean, for our training set, we're essentially just using all the available data from the literature. But so there is a high class imbalance, and we try to overcome this by weighting the different types of classes, essentially. But there is definitely in our training scheme, for example, I think in our original classifier, we only had about 100 RLI arrays and Cepheid stars, which is quite low compared to, let's say, 2,000 rotational variables or something. So by weighting it, we try to overcome that. But ideally, what we're also doing is we're doing some kind of recurrence step where we classify everything, then we battle the predictions that we're actually getting, and then we add that to our training set, retrain the classifier. And this way, kind of do it as like an iterative process where we update our training set at each step and then feed it back in again. Now, talking a little bit about accuracy. Yeah, I think now it's all overlapping on one slide because it's the PDF version. But essentially, we get about 89 to 95% accuracy depending on the survey we're applying to. So we first started using Kepler data because we had lots of labels available on that. And there we see a higher accuracy, mostly because we understand instrumental characteristics much better compared to TESS. And therefore, there's less noise in our final light curves, and we actually get better classification accuracy. On TESS, it's slightly lower, but we expect this will actually increase a little bit in the future still, as soon as we're actually able to remove these instrumental characteristics better. I think that's one of the biggest bottlenecks compared to Kepler and TESS. We just don't understand everything as well as as Kepler, but this is really a process that's ongoing, and you can already see when you go from the TESS primary mission to extended mission 1 and extended mission 2, actually the light curves have become much better as well in that sense. Now, I think so, as I said before, the first architecture we got about 95% accuracy. With the other one, I think we were about at 90% accuracy. Now, one of the latest projects we're also working on is actually using the TESS light curves to inform what we're going to observe with Plato. So Plato is an upcoming ESA space mission. It will be launched in 2026. I'm showing some nice picture of that here. And TESS has already observed actually this field of view. So what we're doing is we're using our classifiers to classify all the stars that Plato will stare at and essentially inform the Plato mission which stars should be observed. And the reason for that is Plato will not send back the full frame images down to Earth, but it will only send back the light curves or the image stems for specific targets. So therefore, it's limited by the data rate essentially. So we need to decide beforehand or probably during the mission which targets we want to send back to Earth. And therefore, we're using our machine learning classifier to actually build a variability catalog specifically optimized for the Plato field of view and for the type of science they're interested in. Here you just see a nice graphical illustration of everything. So here you can actually see the Plato field of view. So some parts, so you see the blue one. Then here you see the TESS continuous viewing zone, which is at least 1 year of data at a time. You can see a nice overlap. So we get all the TESS light curves, we run our machine learning classifier, and then we kind of build a catalog that Plato can use and decide for the community which stars they actually want to observe. And we're specifically optimizing this for pulsating stars, so people can actually use this to propose stars in a complementary science program. Now, moving a little bit to the unsupervised part now. So, well, everything is showing up at once now again because of the PDF, but essentially what we're trying to do, as I said, we have this high level variability classification that came from supervised variability classification. And then we were looking at a way of how can we actually subcluster this data in an interpretable way. And specifically, we started looking at biomedical data processing. So actually, ECG heart rate variability processing is kind of hidden behind this thing, so I can show you. But essentially, we saw that there were some similarities between ECG data and light curves. And then we discovered the multi-scale entropy, and this metric is actually a complexity metric that assesses the complexity of the time series across different time scales. And then we tried to apply this to stellar variability light curves, and we saw that actually was working great. So originally, they used it to distinguish healthy patients from sick patients based on the heart rate. And now we're actually using it to distinguish different types of pulsating stars. Now here I'm showing the overall methodology a little bit, so you can see just these are the light curves we have, 2 types of pulsating stars. You have delta Scuti light curves. These are higher frequency pulsators. These are gamma Dor light curves, lower frequency pulsators. We calculate this multi-scale entropy curve. Essentially, it's 10 data points, where we calculate an entropy metric at each time scale, and then we kind of run a low-pass filter on the time series, and then we calculate another entropy metric. Now then we get all these different 10-dimensional multi-scale entropy curves. We apply UMAP to it to reduce the dimensionality to 2, and then we run HDB scan to actually cluster the data. And here I'm showing you an example, which I'll enlarge in the next slide.
Quick question, to calculate that entropy, do you use different periods and fold the...
So we just take the light curve and then we run some kind of low pass filter. Essentially, you kind of remove variability at shorter time scale and you go to higher and higher time scale by doing some averaging strategies on the light curve itself. And then you calculate each one of those new light. So you calculate essentially 10 different versions of a light curve, and at each version you calculate an entropy metric essentially. And this is like, for example, one of the clusterings we get here. So you can see it's nicely separated. So these are 2 types of pulsating stars. Both of them are, so you have essentially on one hand delta Scuti stars. On the other hand, you have hybrid pulsators, which have both delta Scuti and gamma Dor type pulsations. And the interesting about these hybrid pulsators is that they can actually be used to study both the outer envelope of the stars and the near core properties of the star. And that's why we specifically applied it to this thing. But one of the actually very interesting things we found is with this methodology, we originally developed it for clustering, but we saw that we actually found a correlation between some of the physical properties of the stars. So starting at the right plot, We did the same methodology with this multi-scale entropy curve for a set of gamma dark pulsators. But this had kind of an elongated clustering structure. So we kind of took a look and see, okay, where is the structure coming from? And we found that it was actually strongly correlated to the near co-rotation rates, which is determined through asteroseismology. So actually the fill plot is highly correlated to the specific physical parameter, which is very interesting. So essentially in our methodology, we showed a little bit that we are able to capture some of these physical properties. And now we haven't started on this part yet, but essentially we could use this information to try to predict the rotation rates as well, for example. Now we also did the same thing. We took the structure, but we color-coded to the V sin I, so the surface rotation rates, which are spectroscopically defined. This one is a bit more sparse just because we didn't have as many V sin I observations compared to the astroseismically defined ones, but you see this same kind of structure as well. So it's correlated to both the astroseismic near co-rotation rates, which is purely based on the time domain, and the spectroscopic V sin I rotation rates, which is quite interesting as well. Now, this actually led us to think, okay, if our methodology can capture some of the physical properties, both spectroscopically and from a time domain point of view, why don't we start developing a more complete multimodal model? Specifically, we started looking into the idea of combining spectroscopic data from big surveys, such as, for example, Galah, together with all the information that we have from TESS and also from Kepler, and merge it essentially into some kind of shared embedding space, kind of putting the basis for a big foundation model. Now, this is what our data space essentially looks like. So you have all these different types of surveys. You have on the bottom, you have TESS, and then you have many observations for the same star. One star can be observed in multiple sectors. We take all of these observations, then we add all the available spectra from different catalogs, starting with, for example, Galah or SDSS. So this project is still under development. We just started a couple of months ago, and then we add the data we have from Kepler as well. Now, here I'm showing what such a embedding would look like. So it's essentially based a little bit on the AstroClip paper, which François Lanus developed. But what's novel in our architecture is that we also try to add an instrumental component. So we try to disentangle the instrumental characteristics of the light curve at the same time as well. So we have these different surveys. You have the TESS light curve, then we essentially have a light curve encoder. We have the Kepler light curves. We have another light curve encoder, and then we have the spectroscopic data from one survey, and then we add another spectra encoder. And we get essentially the shared embedding space. And the idea is that this embedding space actually captures the physical properties of the variable star as well. So you can actually use this to do multiple downstream tasks. Specifically, we're interested in the stellar parameter estimation, for example, those near co-rotation rates, or you can also use it for clustering of stellar variability if we actually optimize this latent space for that. And here, as I'm showing, we actually add instrument encoders as well. So once we have these light curves, before we need to disentangle the instrument port from the actual physical point as well. And this is, as I said, quite important for TESS because there are still so many instrumental characteristics in that. Now, showing an example of such instrument modeling. Here, one of my colleagues at MIT actually developed, together with one of the students, the scattered light in TESS. So essentially, you can see here, this is the original image, and it's kind of filled with scattered light. And it's quite annoying to remove from these light curves because it contaminates everything, and we kind of lose a lot of actual information. So by modeling everything in this way, so it's a diffusion-based model, then we can actually here we actually are able to predict the scattered light very well based on angles of the Earth and the Moon, for example, and we're able to predict when exactly the scattered light will be. And this is like one of the things we want to add in our foundation model to actually be able to optimize the physical component of the light curves rather than just the combination of the two of them. So this was maybe one last thing. We're also working actually on the AstroFile project, where we essentially try to. This is actually a big project. We met some people at Flatiron as well, in collaboration with many institutions. But essentially, the idea is here to assemble a massive data set to actually all types of astronomical data, so that it can be used to train foundation models on, and it can also be used for a lot of other different benchmarking sets to, for example, see how well your classifier is doing on a particular data set. So you have a better comparison in that sense. Now, just to conclude, what we're doing, we built a couple of machine learning classifiers here specifically for stellar variability to identify all those different targets. And we use the supervised label essentially as a prior for our unsupervised classification to try to gain more detailed insights into the stellar variability and particularly pulsating stars. And then lastly, one of the recent projects we're into building right now is a big foundation model specifically for TESS variable stars to actually try to capture the physical properties based on a combination of both TESS and Kepler data together with spectroscopic data. So yeah, this was the talk. Thank you.
Thank you so much. Are there any questions?
So this kind of goes back to your multimodal modeling approach, but going back to like the simple classifier or the unsupervised training of the light curves, have you thought about including something very simple like stellar color, right? Because I mean, we know that variability kind of like we know places in the HR diagram, for instance, these stars lie in. So have you tried training on additional metadata other than just the light curve?
I have not, but it's on my to-do list essentially. So it's one of the first things that's on there to actually include different type of color information as well, to actually just use everything that's available, because that will definitely improve our classification as well.
Right.
If you add information like that, we'll get a good increase in accuracy, I think. The idea started at first, I think, just to use light curve information because we wanted to see of that, but now if we add other data, this will definitely increase the classification by a lot, I would say.
You said you were looking at uninterrupted light curves.
Yeah.
How much more complicated does it make for interrupted ones where you go back and look at it later on? Do you expect them to change between them?
So it depends a bit on the type of variability, but essentially we have that in TESS as well. It might be that we have observations for 1 year, and then we don't have observations for the next year for this particular star. But then it depends which type of methodology you're using and whether it's able to deal with these interruptions as well. So some kind of Fourier methods are not optimal for dealing with these gaps, or you might have to adjust some things. I'm not an expert yet in how to stitch those two, but it really depends on the type of methodology you're using for your classification. But essentially, all light curves and TESS have gaps in between. Some of them might be months long, some years long, but then even within TESS, you have downlink gaps as well, for example. But that's just like a day or something. So there, it doesn't matter that much. But then really it goes back to the type of variability or which time scale you're looking at, whether those gaps are a problem or not. If we have very high frequency variability, then it's fine that I would say it's fine that there are gaps. But otherwise, if it's long periodicities that mimic these gaps, then it might be more difficult, I would say.
Any other questions here or online? So could you use the gaps or even cutting them to see what the predictions are for different parts of the same light curve?
Yeah, essentially. So that's also one question what we want to do now. So you have for the same star, you might have observations in 10 different sectors. So then the question is, do you do a classification per sector or do you stitch everything together at once? What the best answer to that is, I don't know yet. At the moment, I'm just using the single light curves, making classification and kind of comparing what the different classifications are for each sector. The nice thing is that you can actually use it to enlarge your training set because you just split it into chunks of 27 days, so we actually get a larger training set. I think in the latest one, we have about 20,000 stars in the training set because we just use all the available light curves per target. But I think for some types of variability, if you stitch the light curves all together in one long light curve, you might actually have better accuracy because the variability is very low amplitude and a very low time scale. So then if you have longer light curves, actually your classification accuracy would improve quite a bit, I would say. But then dealing with these different gaps really depends on the underlying methodology of how you actually, which features do you calculate, for example, to actually do this, or is your self-supervised method able to deal with this? I guess if you feed the time component, essentially the time vector as a component in your methodology, it might be able to deal with this better than just purely stitching everything together.
I mean, that kind of raises the question, can you just go to Fourier space? And like train everything in Fourier space? Yeah,
exactly. So that's also one of the things. So essentially, that's, I think, one of the first reasons as well why in the other methodology, we actually use this image of the Fourier component and fed that into the convolutional neural network, for example. But indeed, I think that's and the other one we're using wavelets a little bit as well. But I think Fourier space is It's a good answer.
I could see you train like a Fourier space and then have like an amplitude or something to encompass like how much variability there is, or some RMS or something like that.
Yeah, exactly. I think that one of the downsides of operating in Fourier space a little bit is that it takes a lot of computational efficiency, yeah, it takes some time essentially, but I think it is a good answer to that question.
Anyone else? Online? I'll keep asking. So in the unsupervised learning, you showed that you can distinguish two classes, is
Yeah.
that right? So what happens with all the other classes?
So I've only applied it to these specific classes because I used I validate this methodology based on an existing catalog of known delta Scuti, hybrid, and gamma Dor pulsators. So I haven't applied it to the other classes, mostly because our team's expertise lied in those two classes, so we just applied it there. But it's actually a very interesting project to actually use this methodology and see where we can actually apply it to. But this feature, so this multi-scale entropy, is actually also fed into one of these classifiers. So essentially, based on that, it's actually able to distinguish some of the other classes as well. So I do have all the different entropy curves. So for the different types for actually all the light curves as well. And I see, especially for these two types, it works well, but it depends really on the type of variability. For some types of variability, it's not optimal, while for others, yeah, exactly.
Because it would be, how difficult is it to compute the entropy?
Oh, it's very easy. There is a public script essentially that I'm just using. So there's some GitHub library where I'm just applying it to the light curve. So it's not that difficult. Just some kind of practical, essentially, it's because it's based on some other more complicated entropy structure. But this is like the one we're using. This multi-scale entropy is a practical, practical calculation that can be used for real world time series that have a lot of noise in them as well, essentially.
So did you only try, what if you're planning to try this on some light curves that are not from variable stars and see if you find new classes? That would be.
Yeah, that would be, so that would definitely be an option as well. So particularly we were actually looking into these two types of pulsation and seeing whether we could find new class in these two high level gamma Dor and delta Scuti class, but you could apply it to other ones as well. I do think it's mostly optimized for distinguishing different types of periodicity. So if you have light curves without any periodicity at all, they might all be in the same bin. So I don't know whether it's the best metric for that one.
Right, but maybe there's some periodicity you just didn't catch.
Yeah.
Like there's some other variables that.
Yeah, exactly.
That are all, maybe you'll have all data points everywhere, but there's going to be a cluster that you just didn't expect.
Yeah, exactly. So that's one of the things we still have to do, just calculate this for all light curves we have. But that's it's not the so it takes a little bit of time to compute all of that thing. But indeed, that's definitely something we should do as well.
For like objects where you have multiple epochs of light curves and you run a classifier and each separate one uses TESS, are there cases where they disagree? And have you figured out whether it's misclassification or it's a weird object?
So there are definitely cases where they disagree. I haven't looked into too much detail yet, but the easiest answer to that is mostly because something went wrong with the light curve processing. So for example, it really depends a lot on the input. If we have perfect light curves, we see it works quite well. But often this is not the case. We have noise, we have scattered light, and that kind of can distort the light curve, especially when it's some kind of complicated variability where it's essentially lying on the boundary between different types of variability. That might make it even more tricky. One of the things in binary systems, for example, you see the eclipses each time, but then that also has momentum dumps. So sometimes, for example, in our initial version, those were not properly corrected for. So all those momentum dumps were just classified as eclipsing binaries. Of course, now that's adjusted by removing the flags. This is one of the things that can just happen. You have in the scattered light, there's significant increases there. So if that's not properly corrected for, then it will be identified as a certain type of variability.
So how does it work when you have two different types of variability on the same star?
Yes, so ideally we get 50-50%. So we get a 50% probability that's a binary system and a 50% probability that's a pulsating star. And we've actually seen that in some cases this is true. So this is possible to actually, it works, but it's not always the case. Sometimes if it's spread out across all different types of variability, so if we have 1/8 probability for each type of class, usually because the classifier doesn't know at all what to do. But if we look at two types that we know can occur together, then we actually see that it works quite well, and this 50-50% probability or 40-60 or something actually holds. And it actually, so we just need to do a search for binaries in combination with, for example, gamma or pulsators.
I have another one. Is that okay?
Yeah.
For the diffusion model, if you go from the image to, you use a diffusion model to get a cleaner image, one of the problems is that diffusion does not conserve flux or anything. So what do you want to?
So I'm not an expert in the diffusion part because it was developed by my colleague essentially. So I'm not sure how exactly they deal with that. Essentially. Also, one of the things you have to, if you use it on the full frame images, I think you have to redo the light curves as well probably. But I'm not sure exactly how their methodology works on that front.
Anyone else? Online? Okay.
Yeah, sorry, we've got one. Alexandra?
Hi, yeah, thanks for your talk. This was super interesting. I might have understood this incorrectly, but I think when you were showing your results from the unsupervised classifier, I saw you had a not assigned label, and I'm just curious what that means.
So that label is actually assigned by, let's see what I can do. Yes, so this label is actually assigned by HDB scan. So this is from the clustering algorithm. And it's essentially because this clustering algorithm, HDB scan, relies on the density of the data points. If the data point is too far out, it will just get a not assigned label. So you can kind of you can change the parameter of the clustering algorithm as well. But it really is just HDB scan. If it's not in a dense cluster region, it will be not assigned, but that might actually be interesting because you can actually use these not assigned ones, see that they're actually further away from everything else. And in that sense, they might be anomalies or different types of variability that you could use because there's no cluster to be found for those specific types.
Right. Okay, cool. Thank you.
Okay, I think there's no more questions. We can wrap up and have lunch.
Perfect.
Thank you very much.